I hope that at some point in your life, you've seen or will see a total solar eclipse, when the moon goes right in front of the sun, blocking it rim to rim. Here's an image from the eclipse of August 21st, 2017, which was seen by millions of Americans. It was amazing. In the minutes beforehand, the sky went from an ordinary bright blue to a silvery twilight. It felt unreal, like we were on a Hollywood stage and someone was turning down the spotlights. And then the sun went black. A solar eclipse is a breathtaking spectacle, but it's also much more than that. After this course, you'll be able to calculate the average density of the sun based on the existence of total eclipses and simple observations of ocean tides. It comes out to be 1.4 grams per cubic centimeter. That'll be an important clue for us about how the sun works, why it's so hot and bright. Speaking of stars, if you're ever in the southern hemisphere on a dark, clear night, look for Omega Centauri. It looks like a little blurry fuzzball. A good telescope reveals that it's actually a cluster of what seems like zillions of stars arranged in a spherical pattern, like glittering lights in a crystal ball. It's just wonderful. But what the picture doesn't show is that these stars are buzzing around like bees in a swarm, some with speeds of 8 kilometers per second. Soon you'll understand how we know that and how it tells us that this cluster has the mass of 4 million suns. Toward the center, all the stars blend together, but if we look even closer, we see a dazzling array of colorful stars: red, blue, yellow, some bright, some faint. And as you'll see, we can use those measurements of color and brightness to deduce how big these stars are, how long they've been shining. Just to forestall suspense, it's about 12 billion years. Next, feast your eyes on this entire galaxy, a golden whirlpool of stars decorated with blue baubles. You would think that such a masterpiece would have a special name. But in fact, galaxies like this one are so common that its only name is a catalog number, NGC 6753. Together, we'll explore these spiral galaxies and learn how to calculate their masses and understand why we think they have giant black holes at their centers. And finally, have a good look at this image. This is what you see with the Hubble Space Telescope when you point it in any random direction of the sky and stare for long enough. At first glance, it looks like a bunch of stars, but when you look closely, you see these lights are entire galaxies, each one with trillions of stars. Zooming in, we see that some of them are spiral-shaped, like our galaxy, but some are more blobby, and some are streaky and have irregular shapes that defy description. By the end of this course, you'll understand how we know that all of these galaxies are rushing away from us, some of them with speeds that seem to exceed the speed of light. And you'll be able to use those measurements to calculate the age of the universe. I hope these examples whet your appetite. In this course, we'll encounter all the wonders of the universe, but we will not be content with just admiring them. We will ask why and how, and we will not be satisfied until we have a deep, quantitative understanding. Welcome to Astrophysics. I chose that word carefully, astrophysics, not astronomy. The two words are basically interchangeable these days, but there is a subtle intellectual distinction. Astrophysics is the application of the laws of physics to understand celestial phenomena. Occasionally, as we'll see, we even discover a new law of physics by studying what's out there. Astrophysics began in the 17th century with Isaac Newton, who explained the motion of the planets with his shiny new equations relating force, mass, acceleration, and gravity. The actual word astrophysics is more recent. It's from the mid-19th century, after the invention of photography and spectroscopy. Those two techniques were crucial because they allowed us to go beyond looking through telescopes with our eyes. Now we could make more objective records, detect fainter sources, and connect our observations to laboratory experiments with light, heat, and atoms. In contrast, astronomy can be defined as the careful observation of heavenly bodies, a cultural activity dating back thousands of years, which only gradually became scientific. The ancient Babylonians, the Chinese, and the Mayans were all accomplished astronomers, but they weren't astrophysicists. There's also an important practical difference between the terms astronomy and astrophysics that you should know about, having chosen this course. Say you meet someone at a party, or you're sitting next to someone on a plane who asks, "What do you do in your spare time?" You have a choice. If you want to be friendly, say you're studying astronomy. You'll have a lovely conversation, although there is a risk you'll be asked about a horoscope. If you want to sound impressive, say you're studying astrophysics. That sounds fancier, doesn't it? That's why astrophysicists turn up in the movies sometimes, like in Top Gun, when the Kelly McGillis character had a PhD in astrophysics. And if you're not feeling sociable, just say you're studying physics. The conversation will come to a screeching halt. I love astrophysics for so many reasons. One of which is that no other science spans such a vast range of scales, from nanometers to billions of light years. From the radiation of a single electron to the output of trillions of suns. In my previous course on planets, it was useful to make a scale model of the solar system, with everything shrunk down by a factor of almost 1 billion. The sun would be a sphere as tall as I am, and the Earth would be like a grape located 2.5 blocks away. That worked well to put the solar system into perspective. But this approach fails utterly when we try to put the whole universe into perspective. Even if we scale everything down by a factor of 1 billion, the very nearest star to the sun would be 25,000 miles away. And our next door neighboring galaxy would be 20 billion miles away. You see, no matter how much we try to scale things down to a manageable size, we still get mind-boggling numbers. The problem is, there's no one scale factor that'll put all the phenomena we're going to study into a mentally comprehensible map. So we need to get comfortable switching our perspective back and forth from one scale to another, from the micro world to the cosmos and back again, without getting dizzy. Let's start practicing by zooming out. We'll start with a map of the teaching company headquarters here in Chantilly, Virginia, where the scale bar represents 100 meters. If we expand our field of view by a factor of 10, so the scale bar is now 1,000 meters, a kilometer, we can take in the whole city. Let's zoom again, another factor of 10. Now we start to see regional features like Chesapeake Bay. Taking another step, our scale bar is 100 kilometers, and we can see the entire mid-Atlantic seaboard. Another factor of 10, and we can see the entire Earth hanging in empty space. At this point, we've zoomed out from hundreds to millions of meters. That brings up the issue of units of measurement. Sometimes we'll want to use standard metric units. For lengths, that would be meters, along with millimeters, kilometers, and so on. The scale bar I've just drawn on our map is 1,000,000 meters long, or 1 megameter. Another way to write that is with scientific notation. 10 to the 6 meters, since 10 to the 6th power is 1,000,000. But other times, we'll want to use units that are more appropriate for the scale we're interested in. When we're thinking about entire planets, meters are not so convenient. It's better to measure things in units of, say, the radius of the Earth. One Earth radius is defined as 6,378 kilometers. That way, we can say the planet Neptune has a radius of about 4 Earth radii, and Jupiter's is about 11. 4 and 11 are much easier to comprehend than however many millions of meters. That's why the Earth radius is a handy unit. We'll write it as an R with a subscript that's a little plus sign inside of a circle. That's the astronomical symbol for Earth. The next useful unit that we'll need is for the size of stars rather than planets. So let's zoom out and zip inward to the center of the solar system so we can take in the entire sun. Its radius is about 700 million meters, or a little more than 100 times bigger than the Earth. Here's what the Earth would look like if it were right next to the sun. The solar radius will be our unit of choice when we discuss stars. We'll write that as R with another astronomical symbol. This time it's a dot inside of a circle. Let's keep zooming out. Once we get to the scale of 10 to the 13 meters, most of the other planets come into view. We've reached the scale of the solar system. On this scale, the scale of planetary systems, the traditional unit is the radius of Earth's orbit around the sun. In fact, that's such a useful unit, it's called the astronomical unit, or AU. It's about 215 solar radii, or 150 billion meters. And with the AU, we can easily describe the solar system. Mercury is about 2/5 of an AU from the sun, and Jupiter is out at 5.2 AU. We're still not done zooming out, though. Far from it. When we expand our scale again beyond the solar system, we find ourselves in empty space for quite a while, until we get to 10 to the 16 meters. Then, at last, some of the neighboring stars come into view. A good unit to use on this scale would be the light year. That's the distance that light travels in 1 year, which is just short of 10 to the 16 meters. For example, the nearest star, Proxima Centauri, is 4.2 light years away. But in practice, astrophysicists don't use light years, except when we're giving public lectures. The preferred unit is called the parsec, and it's about 3.3 light years. We'll see why parsecs are more convenient a couple of lectures from now. What's important for now is that the typical distance between stars is a parsec or two. From here, we need to zoom out by 4 more factors of 10, 4 more orders of magnitude, until the architecture of the Milky Way galaxy comes into view at around 10 to the 20 meters. And at this stage, we'll stop inventing units with idiosyncratic names. We'll just keep using parsecs, but with metric prefixes, like kilo for 1,000. The diameter of a typical spiral galaxy is 10 or 20 kiloparsecs. We've still got some ways to go. It takes a couple more orders of magnitude to start seeing neighboring galaxies. The typical spacing between galaxies is a few megaparsecs, millions of parsecs. After another step, we see that the galaxies themselves group together to form clusters of galaxies, joined by what look like filaments or webs of galaxies. And when we keep going, when we keep increasing the scale bar all the way to 10 to the 26 meters, the universe starts to look like random static, nowhere different from anywhere else. The natural scale here is the gigaparsec, billions of parsecs. That's the end of the line. That's the largest spatial scale about which we have any direct knowledge. By zooming out 26 orders of magnitude, we have a view of the entire observable universe. I've made a chart to summarize what we've just learned. The left-hand column tells us what scale we're on: planets, stars, planetary systems, between stars, galaxies, between galaxies, and the observable universe. The next column tells us the most appropriate unit for that scale, and then the column after that gives the approximate value in meters. And the last column tells us how much bigger that unit is compared to the previous one. One solar radius is 109 Earth radii, and 1 AU is 215 solar radii. There's something interesting about that last column. All the natural scales are separated by factors of order 100 or 1,000, except the middle row, the parsec, the scale in between the stars, is 206,265 times bigger than the AU, the scale of planetary systems. What that means is that stars and their planets are unusually isolated. The spacing between them, relative to their size, is larger than for other types of astronomical objects. This has the fascinating implication that collisions between galaxies are common, but collisions between stars are vanishingly rare. Even when two entire galaxies are colliding, there's not much chance that any two stars inside those galaxies will hit each other. Now, let me tell you about another tactic astrophysicists use to cope with all these orders of magnitude. We make logarithmic maps. First, I'll remind you that taking the logarithm of a number means expressing the number as a power of 10 and then plucking out the exponent. For example, 1,000 is 10 to the third power, so the logarithm of 1,000 is 3. The log of 1,000,000 is 6. And this works for numbers smaller than 10 too. The number 1 is equal to 10 to the 0th power, so the log of 1 is 0. 1/10 is 10 to the minus 1 power, so the log of a tenth is -1, and so on. So, what is a logarithmic map? An ordinary map is based on a single scale factor. 1 inch on the map might be 1 kilometer in real life. But on a logarithmic map, the scale factor changes as you move from one end to the other. The first inch might correspond to 1 meter in real life. But then the second inch is 10 meters, then 100 meters, 1,000, 10 to the 4, 10 to the 5, and so on. Mathematically, with every inch, we increase the logarithm of the scale factor by 1 unit. There's a great example of a logarithmic map in the hallway of our astrophysics building at Princeton University, courtesy of my colleague, Richard Gott. You start at the surface of the Earth, and your first footstep corresponds to 1 Earth radius. And then each one after that is magnified by a factor of 10, so you can traverse all the important scales of the universe, from planets to stars to galaxies to the entire universe, as you walk to class. We're also going to want to make other logarithmic charts besides maps. We'll use logarithmic timelines. And we'll make more abstract logarithmic charts to help us understand things that range over many orders of magnitude. For example, our galaxy is full of objects ranging widely in mass and in size. Among other things, we have asteroids, moons, planets, and stars. So let's say we go around the galaxy and measure the mass and radius of everything smaller than the Sun. To compare all these things, we'll make a chart of mass versus radius. Here are the results on a regular chart. The horizontal axis is mass in units of Earth masses, and the vertical axis is radius in units of Earth radii. Each data point shows the mass and radius of a single object. It looks interesting. There's clearly a relationship between radius and mass. The more massive the object, the bigger the radius, which makes sense. But there's a problem with this chart. Because we needed to make the axes range high enough to encompass the very largest objects, millions of Earth masses, the more numerous, smaller objects end up crammed in close to the origin, and we can't make out the details. Let's remake this chart with logarithmic axes. The horizontal axis is still telling us the mass, but now each tick mark represents a factor of 10. So the Earth is here at 1 Earth mass, 10 to the 0, and the Sun is at a few 100,000 Earth masses, which is 10 to the 5.5 power. So the data point for the Sun is 5.5 ticks to the right. Likewise, the vertical axis still tells us the radius, but on a logarithmic scale. You see how all the little tick marks get scrunched up? That's the effect of the changing scale factor. Let's see what our data set looks like on this logarithmic set of axes. Wow, this is a much better view. We can see all the data clearly. And even better, we can see some patterns that were hidden in the ordinary chart. There are 4 different groups differing in the relationship between mass and radius. For the lowest mass objects, we can draw a straight line through the points up until about twice the mass of the Earth, at which point the pattern changes. The size starts going up more rapidly with mass. The line connecting the dots has a steeper slope. Then at around 100 Earth masses, this relationship changes again, it flattens out. And finally, at around 20,000 Earth masses, the size starts rising again with mass, more rapidly than in any other part of the chart. To get oriented, let's light up the data points for all the planets in our solar system. Together, they span the first 3 groups, and the Sun is in that 4th group. In each of these 4 zones, we can fit the data, at least approximately, with a straight line. What does that mean? Well, on a regular XY chart, a straight line means that y equals ax plus b, where a is the slope of a line, and b is a constant, the y-intercept. That's a linear relationship. But on a logarithmic chart, a straight line means there's a linear relationship between the logs of the variables. Log x equals a log y plus b. Or in this case, the log of the radius equals a times the log of the mass plus a constant. And what does that tell us? It'll be clearer if we solve for r. We can do that by taking the inverse log of both sides. That is, we'll take 10 to the power of each side. On the left, we have 10 to the log r, which is just r, as we wanted. On the right, we have 10 to the power a log m plus b. Now we need to remember some other facts about logs and exponents. When we have a sum in the exponent, we can split it into a product. We can rewrite the right side as 10 to the a log m times 10 to the b. And another fact is that a log m is equal to the log of m to the power a. So the antilog of a log m is m to the power a. The net result is that r is proportional to m to the a power. That kind of relationship is called a power law. One variable is proportional to another one raised to some power. And, evidently, when Mother Nature creates objects in our galaxy, she uses 4 different power law relationships between radius and mass. Let's measure the slope, the value of a, in each of these 4 zones. For the lowest mass objects, the slope is about 1/3. That means r is proportional to m to the 1/3 power, the cube root of m. Now, this low mass regime is closest to the one where we have direct experience, small things like rocks and boulders. So, does this relationship make sense? What do we expect for the relation between radius and mass of everyday objects? Well, it should depend on the density of whatever material it's made of. Let's use the Greek letter rho for density. Rocks have a certain characteristic density of about 2 or 3 grams per cubic centimeter, and mass is equal to density times volume. For a spherical object, the volume is 4/3 pi times the cube of the radius. So we expect m to be proportional to r cubed, or inverting that, r is proportional to m to the 1/3 power, which is what we see in the chart. So, great. We can understand the objects that have masses lower than 1 Earth mass. They behave like rocks. Now, in the second zone, we find a slope of about 1/2. R is proportional to m to the 1/2 power, which is bigger than 1/3. That means that the more massive objects have larger radii than we would have expected if they all had the same density. So it must be that the more massive objects are less dense. The most massive objects in this zone must be a lot puffier and less dense than rock. Which is true. These are the gaseous planets, like Uranus, Neptune, and Saturn. In this zone, the planets have a lot of hydrogen and helium gas, very lightweight elements, in addition to rock. By the way, the other data points in this zone are planets that we've discovered around other stars, exoplanets. We'll have a lot more to say about them in a later lecture. Now let's look at the third zone. Here, the line is horizontal. The slope is 0. The size hardly changes at all, even when we increase the mass by a factor of 100. I hope you agree. This is really weird. In everyday life, when we pack more mass onto a ball, the ball gets bigger. But apparently this is not the case for balls between 100 and 10,000 Earth masses. Our own Jupiter is in this zone, as are lots of exoplanets. What must be happening here is that the more massive objects are much denser than the less massive versions. Why would that be? Are they made of some exotic elements? No, as it turns out, they're mostly hydrogen and helium too. Part of the reason that they're increasingly dense is gravitational compression. These objects are so massive that their own gravity compresses them to higher densities than usual. But the other part of the explanation is a fascinating effect called quantum degeneracy pressure, which we will discuss in due course. There is no single name for all the objects in this zone. Sometimes we call them Jovian planets, although toward the higher mass end, the traditional term is brown dwarfs. Finally, we have the highest mass objects, for which we get a slope of about 1, which means that for these guys, radius is proportional to mass. These are stars, objects for which the gravitational compression is so strong that nuclear fusion ignites at the center, creating lots of heat and pressure. This same nuclear fusion also produces the light that stars are famous for. It's what makes stars shine. And one of our goals for later in this course is to understand stars well enough to explain why radius is proportional to mass. There's one final way in which orders of magnitude will pervade this course. Our goal is to understand the phenomena we see through our telescopes with reference to the laws of physics. We're going to need to draw on many areas of physics: mechanics, gravity, radiation, quantum theory, relativity. That's part of what makes astrophysics so much fun. It ties everything together. The practicing astrophysicist needs to learn how to perform detailed calculations in all of those areas. But to understand something, you don't necessarily need to get all the details right. This course is not about how to do research. We don't need to fit all the data points exactly. And we're not building a spacecraft. We don't need to calculate trajectories to 6 decimal places. What we want to do is understand the basic physics that determines the order of magnitude of a phenomenon. Why is the sun 100 times bigger than the Earth? Why is a white dwarf 1,000 times bigger than a neutron star? How do we know the universe is billions of years old as opposed to millions or trillions? For these kind of questions, we don't always need complex calculations. In fact, they often inhibit our ability to understand something for the first time. I'll need to rely on your knowledge of math, things like logarithms and trigonometry. I'll also rely on first-year college physics F equals ma, the law of gravity, the wavelength and frequency of waves, and that sort of thing. Sometimes I will go deeper. I'll use vectors, I'll take derivatives, which I hope will be helpful and rewarding for those of you who've studied more math. But if not, don't worry. I promise to do my best to help you understand the results, even if you don't follow every step. Most importantly, I'm going to count on your curiosity, your desire to understand deeply, your patience for learning new things, and your sense of wonder. See you next time.